In our previous lecture, we introduced our new nonlinear component, namely operational amplifier. We talked about its model, and we started analyzing some simple circuits that contain an operational amplifier. In particular, we obtain the input-output voltage relationship for the voltage follower. Okay, a very simple but useful op-amp circuit. Today, in this lecture, we will continue with further examples. Our first example in this lecture is called inverting amplifier. Okay. This is the circuit. Now, we'll try to figure out the relation between the input voltage here and the output voltage. Input is connected to the device through these two resistors, R1 and RF, and F is for feedback, because we're feeding the output information through this resistor back to one of the input terminals. So unless otherwise stated, we will always be working with the infinite gain ideal op-amp model, where the input currents are taken to be zero. Okay, so there is no current escaping into the op-amp from these two terminals. And in linear region, it's this voltage and that voltage, they are equal. V plus equals V minus according to our model. Okay, and for the saturation region, this V plus is larger than V minus, and for the negative saturation region, V minus is larger than V plus. And at saturation regions, the output is fixed at the saturation voltage. Okay. So how we go with the analysis for such circuits is very simple. We said what we do is we obtain this voltage, node voltage, V minus, in terms of input and output voltages. Okay. And we likewise we obtain V plus, or we obtain expression for V plus in terms of, again, V output and V input voltages. And then we start our analysis, region by region analysis. In linear region, we have V minus equals V plus. Then equating those two expressions in terms of V in and V out, we obtain a relation between input voltage and output voltage. And then we take that output voltage in terms of input voltage and put it into the constraint under which the op-amp is in linear region, and from there we obtain a constraint, or we translate that constraint into a constraint in terms of V in, so that the op-amp is in linear region. And then we do similar analysis for the saturation regions. Okay, so therefore the first step, or perhaps the 0th step, is obtaining V minus and V plus in terms of the input and output voltages. Okay, so let's write KCL at this node. Okay, V minus minus V in over R1. Okay, so this node voltage is called V minus. So V minus minus V in divided by R1. We're talking about this current. Okay, plus this current, which is V minus minus V out over RF, and finally plus this current must equal 0. But this current, which sometimes called I minus, according to our model, well, in practice that current is so tiny that it's okay to take it, and according to our model we take it to equal 0. Okay, so therefore there is no current escape to the op-amp from one of the input terminals. Hence, this plus that plus 0 equals 0. Okay. And from this KCL expression or the node expression, we can clearly obtain V minus into as a function of V in and V out. Okay, so let's do that. 1 over R1 plus 1 over RF. V minus equals 1 over R1 V in plus 1 over RF V out. Therefore, V minus equals 1 over R1 plus 1 over RF inverse times 1 over R1 V in plus 1 over RF V out. Okay, so let's call this equation 1. So what we did is we obtained V minus, this known voltage, in terms of the output and input voltages. And note that when writing these equations, which well, basically we just wrote one equation, it's KCL, we didn't have to make any assumption on what region the op-amp is operating in. Therefore, this relation that we have found must hold at all regions. Okay, so that's a region-free operation. Now we're going to do the same thing for V plus, that is express V plus in terms of V in and V out, but that's for this topology is just trivial because V plus, this node is directly connected to ground, therefore V plus equals 0 at all regions. That's our expression of V plus in terms of everything, but in this case it's just 0. And note that 1 and 2, those two equations, they're true for all regions, are valid in all regions. Okay, so we're now ready to begin our region by region analysis. We start from the linear region, where V minus and V plus, they're equal, or the voltage difference between V plus and V minus 0, and the output voltage is in between negative and positive saturation voltages. Okay. Now, what's V minus? V minus is here. So let's write that down. 1 over R1 plus 1 over RF inverse 1 over R1 V in plus 1 over RF V out. So that's our V minus. It holds at all regions, therefore it holds in linear region, and that equals V plus. And what's V plus? V plus is 0 because this node is connected to ground directly. Equals 0. And once you write that equation down, you immediately obtain the relation between the output and input voltages. Therefore, V out equals minus RF over R1 V in. Okay. Now, this relation between output and input voltages doesn't hold for all input voltages, and now we have to figure out for what values of input voltage this holds true, or in other words, for what values of input voltage this op-amp remains in linear region. For that, what we do is we take this V out in terms of V in and put it into that constraint inequality. And minus ES less than equal to V out in terms of, okay, and that's less than equal to ES. Here we're going to put V out, and V out we know in terms of V in. So let's put that down. Minus RF over R1 V in. And that means ES less than equal to V in less than equal to R1 over Rf ES. Okay. And with this, our part of analysis corresponding to linear region is complete. What we have figured out is the relation between input and output voltages and the condition under which, okay, the condition in terms of input voltage under which that relation is valid. Okay, so the analysis for linear region is complete. Now what we're going to do, we're going to move on to saturation regions. Okay, positive saturation region. This is the condition, V minus less than V plus, and there's nothing to compute about the output voltage because at positive saturation the output voltage is fixed. It's constant at the saturation voltage, ES. Okay. Now, therefore, by analysis of positive saturation, all we need to figure out is we need to figure out the condition on input voltage so that the op-amp is in positive saturation region, or the output voltage is fixed at ES. Okay. For that, what we do is we go and take the expression of V minus and V plus in terms of V in and V out. Now, V out is fixed at ES, therefore we replace V out with ES, and therefore everything would be in terms of V in. Okay. And that's what we need. We need a condition on V in so that the op-amp is in positive saturation region. So what's V in? Excuse me, what's V minus? V minus is 1 over R1 plus 1 over Rf inverse 1 over R1 V in plus 1 over Rf V out. Okay? This is the same relation that we used here, because that V minus being equal to that holds true for all regions. Now, instead of writing V out, we directly write ES because we're considering the positive saturation region. Yes. Okay, so in positive saturation region, this is what V minus is. And that has to be smaller than V plus, and V plus is 0 at all regions because of the connection. And this is the condition on input voltage for which the op-amp is in positive saturation region. So let's write this down a little bit simply. Okay. That means that provided that V in is less than minus R1 over Rf ES, the op-amp is in positive saturation region. And as for negative saturation region, V minus must be larger than V plus, and there is nothing to compute about the output voltage. It's fixed at minus ES. And using a similar argument, in fact the same argument that we use in the positive saturation region analysis, we can directly write that V in greater than R1 over Rf guarantees that the op-amp is in negative saturation region. So, we have therefore completed our analysis. This is the input-output relation for the linear region under the condition that input voltage is in that range. This is the condition on input voltage so that the op-amp is in negative saturation region. And finally, this is the condition on the input voltage so that the op-amp is in positive saturation region. Let's combine those three pieces of information into a single visual whole. And if you do that, this is what we obtain. Okay. So V in, V out. That's the origin. So what happens is, again, the relation between input and output is linear in the linear region, but with negative slope. With voltage follower, the slope was positive. In fact, the slope was 1. Okay. This is the relation between input and output voltages, provided that output is in between ES and minus ES. Then, when Vin is larger than something, okay, therefore we're going toward right, the op-amp is in negative saturation region, and when Vin is smaller than something, the op-amp is in positive saturation region, and here the slope is minus RF over R. Minus RF over R. This is the input. This is the transfer characteristics. Okay. Now let's talk about another circuit. Now here, this is called an inverting amplifier, partly because the slope in linear region is negative. Now we're going to be talking about non-inverting amplifier. Not surprisingly, we're expecting a similar shape, similar curve, but with positive slope in linear region. And for that, this is the topology. So the op-amp without minus plus begin R1 or feedback. This is topology. Input now is being introduced to apply to op-amp from the non-inverting input, and again we have some feedback connection, and the other end is connected through R1 directly to ground. Let's figure out the relation between input voltage and output voltage for this circuit. As before, what we do is we write down V plus in terms of input and output voltages. In this case, it's very straightforward. V plus directly equals V in. And we write V minus in terms of input and output voltages. And that's also fairly simple, which we're going to do now. Then once we have V minus and V plus expressions in terms of V in and V out, we can start our region by region analysis. Okay, the procedure is simple. Again, by KCL, at this node, V minus over R1, okay, this current, plus that current must equal to 0. Note that because we're working with the ideal model, this current into the op-amp through the terminal is 0. Okay. How about this current? This current is V minus minus V out divided by the resistance in between. So that means V minus equals 1 plus RF over R1 inverse V out. Okay. So V minus depends on V out as such. We didn't make any assumptions depending on the region of the op-amp. Therefore, that equation holds true at all regions. And how about V plus? V plus trivially equals V. Again, the region-free equation. Now we're ready to ready for our region by region analysis. Linear region, where V minus must equal V plus, and the output voltage lies between minus ES and plus ES. Okay, so what's V minus? V minus is 1 plus RF over R1 inverse V out. Okay, V minus equals that in terms of V out. Equation 1. What's V plus? V plus is V in, again, a region of the equation. Then we have V out equals 1 plus RF over R1 times V. So the output depends linearly on input voltage in linear region, and the slope here this time is positive. Well, we're working with passive resistors. So this is the relation. We have to figure out one more thing, and that's the condition on input voltage under which this relation holds. For that, we take this minus ES, okay, then it's less than or equal to V out, and that's less than or equal to ES. But instead of writing V out in the middle, what we do is we write V out in terms of V. 1 plus RF over R1 V. And then we have what we want, minus 1 plus RF over R1 inverse ES less than or equal to V in, and that's less than or equal to 1 plus RF R1 inverse ES. Okay? So this is the condition which guarantees that the relation between output and input voltages is that linear equation. Okay? Let's quickly perform the positive saturation, negative saturation region analysis, and we'll be done. Okay, positive saturation region, V minus smaller than V plus, and V out is fixed at positive saturation voltage. Yes. To translate this condition into a condition in terms of input voltage, what we do is we write V minus 1 plus RF over R1 inverse times V out, that's equation 1, and V out in positive saturation region is ES. Therefore, times ES is what V minus is when the op-amp is in positive saturation region. And that less than V plus, and V plus is V in at all times, and that's our conditional input voltage, under which op-amp is in positive saturation region. And similarly for negative saturation region, V minus has to be greater than V plus, and V out is fixed at minus ES. Okay, V minus is this times V out, and V out this time is minus ES. And that should be greater than V in, V plus, and V plus is V in, and that gives us our condition. Minus 1 plus RF over R1 inverse ES greater than V. Okay. So we have all the pieces, the input-output relation in linear region, the condition for that, and that's output voltage in linear region, excuse positive saturation region, and condition for that, likewise, for the negative saturation region. Hence, if you combine those three pieces, this is what you get. V in, V out. A linear relation with positive slope. ES minus ES. Okay, and here the slope is 1 plus RF over R1. Okay. So this, if you look at the circuit carefully, this is no other than a straightforward generalization of what we call voltage buffer. Excuse me, a voltage follower or a buffer. Okay, our next examples will show that operational amplifiers can be used to do mathematical operations with voltages, with signals. Namely, you can do addition, you can do subtraction, you can even do differentiation and integration with very simple topologies. And now we're going to see how that's possible. Let's start with summation. Summing amplifier. Okay. Now, in our previous examples, we had just a single input voltage. In this example, we have arbitrarily many. Okay, all these are individual input voltages, V1, V2, Vn. In a sense, we can consider input this time as a vector, and the output is a scalar. Okay. Now, consider this situation where you have a bunch of signals, okay, a bunch of voltages, and then what you want is you want to add those voltages and obtain some, or more generally speaking, you want some weighted average of those n different signals. And why would you need such a thing? Okay. For instance, consider you have a large conference room, and across that conference room there are some sensors, temperature sensors, and you're collecting data, you're collecting temperature information from different places from that very large room, and you want to compute some average value of the temperature, the average temperature of the conference room. For that, what you have to do is you have to take the average or a weighted average of all those voltages, okay, or all those temperatures. So the sensors collect temperatures, the physical data, convert them to electronic data, okay, electrical data, namely voltages, and then you collect those voltages, obtain an average voltage, which carries the average temperature information. And then you send this to, let's say, your decision-making circuitry, so that you either pump heat to the conference room or you extract some heat from the conference room, okay, depending on your ideal temperature. So let's do the analysis and try to express output voltage in terms of the input voltages. We're going to do only the linear region analysis because this circuitry is designed to work for the linear region. in linear region, what we have is we have V minus equals V plus. Okay, and V plus is directly connected to ground, therefore V minus is 0. Okay. Then using that information, let's now compute individual currents flowing over those resistors, okay, through which we connect the input voltages to the inverting input terminal of the operational amplifier. Okay, the kth current, IK, equals kth voltage minus this node voltage, and this node is node corresponding to V minus over the resistance in between. Now, in linear region, V minus, we saw that equals 0. Therefore, IK is VK over RK. And IF, this current, we can call it the feedback current, is V minus minus V out divided by the resistance in between. V minus is 0, therefore IF is minus V out over RF. V minus minus V out over RF. That's minus V out over RF. Okay. And now we're going to link these voltages to the output voltage, thanks to or using KCL. Now by KCL, all these currents, okay, I1 plus I2 plus up to IN, is the current that flows over this wire, and there is no current escaping into the op-amp through this wire, through this terminal, okay, because input resistance is infinity. That means whatever this current is, it directly flows over RF. Therefore, this current, which is the sum of those n currents, must equal the feedback current, IF. Okay. So we have I1 plus I2 plus IN must equal IF. And translate that equation or express that equation in terms of voltages. So what you have is V1 over R1 plus V2 over R2 plus Vn over Rn equals IF, that is minus V out over RF. Okay. Therefore, V out equals the following weighted average, well, with some minus sign in front, but that's not a problem, of following voltages. RF over R1 V1 plus RF over R2 V2 RF over Rn Vn. So that's the relation between the output voltage and input voltage, provided that op-amp is guaranteed to stay in linear region. Okay, so that's how you do sums. Let's also talk about subtraction. Difference amplifier. Here is the circuitry for that. Now, at the output voltage, we want to see some difference of two input voltages, V1 and V2. So let's begin our analysis. What we do is we write V plus in terms of the input voltage and output voltage. We write V minus in terms of the input and output voltages. And then we equate V minus to V plus to obtain the relation between input voltage and the output voltage. Okay? As in the previous example, we'll be assuming that we're in linear region. Okay, so let's begin by V plus. Okay, what V plus is there's no current escaping to the op-amp here, therefore we can just ignore this line when we're trying to figure out V plus. When you ignore that line, this voltage that appears here can be computed simply through a voltage division. Okay, R3 over the overall resistance seen by V2 must give us the voltage that appears here, which is no other than V plus. So V plus is R3 over R2 plus R3 times the second input voltage V2. Okay. And that's right, that is 1 plus R2 over R3 inverse V2. Let's call this equation 1. Okay, so that's V plus. And then as for V minus, we can write, or we can collect some information by writing node equation in this node. So what we have is V minus minus V1 over R1, this current, plus V minus minus V out over RF, this current, plus this current, which is 0, equals 0. Okay. Therefore, we can write 1 over R1 plus 1 over RF times V minus equals V1 over R1 plus VR over RF. So that's the relation that ties V minus to V1 and V out. Okay. Okay, so then we can write V out as RF over R1, 1 plus R1 over RF, V minus minus V1. Okay, so that's equation 2. Okay, all we did over there is we wrote V out in terms of V minus and V1. Now, in linear region, okay, we have V plus equals V minus. Combining that constraint, V plus equals V minus, together with equations 1 and 2, implies that V out must equal RF over R1. Then we have 1 plus R1 over RF times V minus. And V minus is V plus, and V plus is here. Okay. 1 plus R2 over R3 inverse V2. And then that's, from that we subtract V1. So therefore, V out is something times the difference between something times V2 minus V1. And now if you want the pure difference, that is V2 minus V1, we can achieve that by designing the parameter values. Okay? If you let R1 over RF equal R2 over R3, then this and that, they cancel one another, and the whole thing becomes 1, and we have inside the brackets V2 minus V1. Then choosing the ratios R1 to RF and R2 to R3 same gives us V0 equals RF over R1 times V2 minus V1. Okay, therefore the output voltage, in the output voltage we see something that's proportional to the difference between the two input voltages, V times V1. And this is true in linear region. Okay. Now let's also quickly talk about how one can use an operation amplifier to obtain an integrating device, or integrating circuit, or a differentiating circuit. Okay. Let's begin by an integrator. Which requires that we use a dynamic component, namely a capacitor. Okay, and now in the feedback connection, instead of a resistor, now we place an LTI capacitor with capacitance C. Let's call this voltage VC, the capacitor voltage. This is minus, and this is R. This current is I. Okay. Now, in the output, we want to see some integral of the input voltage. Okay. So, for a constant input voltage, therefore, we see the magnitude of, we want to see the magnitude of the output voltage rising linearly. Okay. Or polynomially, if you want to say. So in linear region, we have the equality V plus equals V minus. And, well, let's write V minus equals V plus. V minus equals V plus, and V plus is directly connected to ground, therefore, in linear region, V minus is 0. Then, what we have is, this current here equals V in minus V minus over R. And since V minus is 0 in linear region, this current simply is V in over R. Okay, I equals V in over R. Equation 1. And this voltage VC equals V minus minus V out. V minus is 0, therefore VC must equal minus V out. Equation 2. Also, let's write down the terminal equation for the capacitor. We have VCT equals initial capacitor voltage VC0 plus 1 over the capacitance, then we integrate the current IC to, okay, this current is the capacitor current. Since the current escaping to the op-amp through this terminal is 0, it means that whatever this current is, exactly the same current flows over the capacitor. Okay, therefore the capacitor current is also I. So we have here I tau d tau. Equation 3. Okay. Now what we do is we combine equations 1, 2, and 3 to obtain relation between input and output voltages. 1, 2, and 3 implies V out of t equals V out 0, the initial output voltage, minus 1 over RC, 0 to t, V in tau d tau. in linear region. And therefore, in the output, we see some sort of an integral of the input voltage. This is called, therefore, an integrator circuit. Let's also talk about the reverse operation, this differentiation. Differentiator. It turns out that all we have to do to obtain that derivative operator, you have to replace this resistor and this capacitor. Swap them. So this is the input voltage. It's connected to capacitor. That's connected to the inverting input. Minus. Here we have ground as before, and the feedback connection now is established by an LTI resistor. R plus minus VC, and the capacitance is C. This is V out. Now in linear region, we have V minus equals V plus. V plus is 0 at all regions. Therefore, this node acts like a ground node in linear region V minus. And what we have is VC equals this node voltage minus that node voltage, okay? So this node voltage is V in, and this node voltage is V minus, and V minus is 0. Therefore, VC equals V in. Okay, so that's one thing. That's one observation. The other observation is, okay, let's call this I, the current. I equals C dVC dt. So that's the terminal equation for the capacitor. And whatever this I is, it's the same current flowing over the resistor over there, because there is no current escaping to the op-amp through that terminal. And VC is V in, therefore C dV in over dt. And finally, this voltage here, which is Ri, equals V minus minus V out. V minus is 0, therefore this voltage plus minus equals minus V out. Okay, V out equals minus Ri. Okay. Now if you get rid of I, the current, in the last two equations, what we obtain is V out equals minus Rc times rate of change of the input voltage. dV in over dt in linear region. And that's a simple way to obtain a derivative operator using an op-amp and a dynamic component.